A startling and sudden event has compelled NASA to enter a state of heightened surveillance. For weeks, astronomers had been closely monitoring the interstellar object known as 3I/ATLAS as it slowly journeyed into the inner solar system. Everything appeared calm until, almost without warning, a sharp spike in hydroxyl emissions erupted within ultraviolet data. This was the unmistakable signature of water being torn apart by sunlight. Initially, teams believed it was a calibration error. At a distance of nearly 3 astronomical units from the Sun, distant comets simply cannot release water at such a rate. Yet the signal continued to swell, wave after wave. Observers soon realized they were witnessing something truly extraordinary. Multiple observatories reported a violent, continuous outburst, completely disproportionate for an object at this distance. One researcher likened the scene to a ruptured fire hydrant in space, a phrase that instantly spread through scientific channels because no one could offer a better explanation. NASA has yet to issue an official statement, but internally the reaction was instantaneous. Routine monitoring shifted to an active alert status. A sudden surge in water loss indicates a structural change, and structural shifts in interstellar objects are among the most unpredictable phenomena in astrophysics. Stranger still is how it began. There was no gradual ramp-up, no steady brightening, no transitional phases that typically precede major cometary outbursts. 3I/ATLAS seemed to click into a new state instantly, as if something beneath its surface had suddenly released pent-up pressure. Scientists examining the raw data are divided. Is this a transient event or the onset of a far more profound evolution? One confirmed fact troubles researchers most. 3I/ATLAS is losing water far faster than any physical model permits at this solar distance. Until NASA understands the cause, no one can predict what happens next. What alarms scientists is not just the volume of loss, but its location. At roughly 3 astronomical units, sunlight is too feeble to drive strong sublimation. Typical comets there emit only a faint haze, their surface is frigid and ice is buried under a thick insulating crust. Yet 3I/ATLAS is ejecting water at a rate of approximately 40 kilograms per second, a figure corroborated by several observatories using hydroxyl emission measurements. At this range, the outflow should be near zero, not a powerful sustained jet. The hydroxyl molecule was the key. When ultraviolet light breaks apart water molecules, it leaves this distinct spectral fingerprint. The intensifying signal around the object declares, "This is not a faint haze. This is a powerful continuous stream of water." All this is occurring while the object receives less than 1% of the solar energy it will encounter later in its orbit. Physically, chemically, thermally, the data defy reconciliation. Such an outburst points to one conclusion. Something internal is forcing the water out: pressure, a sudden fracture, or a freshly exposed icy reservoir. If this were normal cometary behavior, we would see it in other distant objects, but we do not. Solar system comets exhibit such fire hose eruptions only much closer to the Sun, where deep ice is actively vaporized. Here, everything is inverted. The Sun is too weak, the temperature too low, the distance too great for natural sublimation to explain what we observe. Even seasoned comet specialists admit this level of activity is utterly incompatible with thermal models. Each new puzzle, each discrepancy points to one unsettling notion. The surface of 3I/ATLAS is not behaving as we assumed. To grasp why this eruption is so confounding, one must understand what 3I/ATLAS is. This is not a young comet from our solar neighborhood. It is an interstellar wanderer, only the third confirmed object of its kind, a body that has drifted between stars for an estimated 7 to 14 billion years. This journey alone makes it radically different from anything that formed here. While local comets spend most of their lives in the protected cold outskirts of our system, 3I/ATLAS has endured unimaginable eons in open interstellar space, bombarded by galactic cosmic rays. These rays reconfigure matter molecule by molecule. Over billions of years, they bake out light elements, restructure ice matrices, and forge around the nucleus a dark, dense, almost stone-like shell. Estimates suggest this irradiated crust could be 15 to 20 meters thick, far more substantial than on comets warmed by routine solar heating. This implies the icy interior of 3I/ATLAS should be shielded beneath such armor that at 3 astronomical units, sunlight could barely graze it. Under normal conditions, its internal water should remain locked away until the object ventures much closer. Its size deepens the mystery. 3I/ATLAS is significantly larger than the first interstellar visitor, Oumuamua, and far more massive than the second, Borisov. Interstellar objects of this scale are rare. Those retaining deep water reserves after billions of years are nearly inconceivable. Cosmic rays over such timescales should have destroyed virtually all accessible ice, leaving behind only a dry, carbon-rich material. Yet here it is, not dry, not quiescent, not stable, but suddenly venting water like a high-pressure valve. This is the core concern for researchers. Everything about the structure of 3I/ATLAS suggests it should resist water loss at this distance. Yet we witness the opposite. an outburst comparable to those of comets much nearer the Sun. Therefore, something far more profound must have occurred within its nucleus. If the cosmic ray-processed crust has indeed cracked, what lies beneath may be far less depleted and far more volatile than anticipated. The leading hypothesis is simple and unsettling. The ancient shell may have fractured. After 7 to 14 billion years of cosmic ray bombardment, the object's outer layer is theorized to have transformed into an ultra-hard, 15 to 20 meter thick carapace. This shell acts as armor, sealing in interior ices and blocking heat from penetrating deeper. But armor can fail. When it does, the pressure accumulated within has only one exit. A sudden breach in such ancient crust behaves like a ruptured high-pressure valve. Once sunlight touches fresh internal ice, vapor forms explosively. With nowhere else to go, the pressure blasts outward through the weakest point, creating a jet powerful enough to match the cosmic fire hose described by observers. Laboratory experiments on irradiated ices confirm, if the crust cracks, the degassing rate can leap from near zero to explosive in an instant. This perfectly explains the abrupt spike in hydroxyl signals. No gradual rise, no warning, just a sudden, instantaneous switch to maximum power. This scenario also clarifies why the outburst is almost pure water, not carbon dioxide. If the fracture reached deep enough, it could have tapped pristine layers untouched since the object's formation. These inner regions may have preserved primordial water ice, sheltered from cosmic erosion for eons. Such a rupture would release a steam jet unlike anything produced by the long-processed outer layers, a direct look at matter older than our Sun. Yet the cracked crust hypothesis raises new, troubling questions. Why did the fracture happen now? Why at this specific solar distance? And with enough force to breach an insulating shell theoretically impervious without intense heating? Stranger still, the water jet appears sustained, not brief. This hints that the fracture is not a superficial tear, but a persistent conduit reaching deep into the core. If true, the reservoir feeding this vent could be vast. While a single crack may explain the outburst's power, it cannot account for a deeper discrepancy, the difference between the thrust such a flow should generate and the motion we actually observe. Herein lies an even more challenging puzzle. If 3IATLAS is ejecting water at approximately 40 kilograms per second, as observations indicate, this stream should create a significant impulse. Outgassing is thrust. It's rocket physics. When a comet emits mass in one direction, it accelerates in the opposite one. With such a powerful flow, the force should be easily calculable, predictable, and unmistakably evident in its trajectory. Yet researchers do not see this. The acceleration profile of 3IATLAS does not align with the thrust expected from a water jet. Even accounting for previously detected carbon dioxide streams, the resulting vectors leave unexplained deviations. Some of the motion fits the models, but far from all. It is this unresolved remainder that transforms into a new, more serious enigma. The part of the picture that doesn't match calculations most worries mission engineers and orbital dynamicists. The jet is powerful. That's a fact, but it isn't producing the directed momentum it should, according to the laws of physics. Possible explanations exist. An internal fracture might have opened at a strange angle, redirecting thrust. Surface rotation could smear the jet's effect over time. The crust might act as a nozzle, widening or constricting as the core heats. Yet even when modeling these scenarios, a sense remains that something doesn't add up. The numbers refuse to form a coherent picture. The longer the outburst continues, the more apparent the discrepancy becomes. While the object is hidden in the blinding glare behind the Sun, no one can say if the thrust is changing over time, intensifying, diminishing, or being masked by something more profound occurring within the nucleus. For now, scientists have only the stark numbers. Outgassing is real, water loss is immense, and acceleration still doesn't match expectations. It is this rift between theory and reality that prompted NASA's elevated watch.